Good morning everyone, and welcome to today's worked exam answer question. On this sheet of paper we've got two different questions, and I'm going to do this in two parts just to try and keep the videos a little bit more concise. So we're going to be having a look at the top question, question 12, in this particular video, and then tomorrow I will share with you the answer for question 13. So question 12 today is having a look at an AQA A-level question which could appear in either an AS or an A-level paper, because this is content from the Group 7 topic which comes under the AS specification. So we're having a look at the reaction of sulfuric acid with solid potassium iodide, and we've been given an equation for that reaction. We can see that we're making iodine, potassium hydrogen sulfate, hydrogen sulfide gas and water as our four products. And what we need to, understand about reactions of halide ions with sulfuric acid is that we get acid-base reactions occurring for every single halide ion. We get differing levels of redox in terms of there are differing amounts of reduction that the iodide or bromide ion can cause the sulfur to undergo. So the iodide ion is the best of the three that we need to be familiar with, so we get products that reflect that, such as the hydrogen sulfide. And we have to give two observations that we would make when this reaction occurs. State in terms of electrons what happens to the iodide ions in the reaction. State the change in oxidation state of sulfur that occurs during this formation of H2S, and deduce the half equation for the conversion of H2SO4 into H2S. So we're going to be writing a reduction half equation to show how the sulfur's oxidation state changes. And that's worth 5 marks, so we're going to get 2 for our observations, 1 for explaining in terms of electrons, and then 1 for the change in oxidation state, 1 for the half equation. So it's quite nicely set out so that we can see where the marks are going to come from. So in terms of the different products, the KHSO4, that's going to be made in the acid-base reaction, where the H2SO4 will give up a proton to become HSO4 minus and then react with the K plus from the Ki. The iodine and the H2S and the water are all going to be formed during the redox reaction, and they're all going to, well, these two are going to appear in our reduction half equation, and the iodine will be made when the iodide ions are oxidized. So in terms of observations, it's going to be the iodine and the H2S that we are going to notice have been made. The potassium hydrogen sulfate is a white solid. We're not going to be able to see that really forming in the test tube, particularly not when we are making iodine, which will appear as a purple vapour. And when I've done this experiment before, the purple vapour kind of shoots up the walls of the test tube, so then you've kind of got this purple coating, so you can't really then see anything else going on inside the test tube or the boiling tube. H2S is our rotten egg smell, so the smell like the stink bombs that you will have smelled at some point in your lives, I have no doubt. So yeah, bad egg smell or rotten egg smell for our H2S. So those are going to be my 2 observations. So with the reactions of the halide ions with sulfuric acid, we do need to know the differing sulfur containing products that can be made with bromide ions and iodide ions. We also need to know how we would recognise that those products have been made, and also with the iodide ions becoming iodine, what the iodine would look like, and bromide ions becoming bromine, what the bromine would look like as well. So my 2 observations are, so 1, purple vapour / fumes of I2, and then my second observation will be the rotten egg smell of H2S. So that's my first 2 marks done. Then it says state in terms of electrons what happens to the iodide ions in this reaction. Now, if we have a look at this overall equation, we can see that we're going from iodide ions, which they've also told us because we've got K plus and I minus in that compound. Here the iodine is an element, so we've gone back to atoms. So if iodide ions with a full outer shell have gone back to being atoms with, to use GCSE terminology, 7 electrons in their outer shell instead of 8, they have to be losing electrons to go from ions to atoms. If it helps, you could write a half equation to figure that out, or we could have a look at the oxidation states to help us figure that out as well. So the oxidation state of the I minus ion is -1. The oxidation state of any element, is 0. So going from -1 to 0 is an increase in oxidation state, and an increase of oxidation state is oxidation. And so if it's oxidation, electrons have to be being lost. So there's a couple of ways we can figure that out. But the key thing is we have to then state in terms of electrons what happens. So the iodide ions, really important that we don't say the iodine ions. Don't know what my brain was doing there. So the iodide ions will each lose 1 electron. That's going to be all we need to say because it says in terms of electrons, but for your guys' benefit, I will add as they are oxidized, so you know that's what's going on. So again, just for a little bit of context for you guys, if the iodide ions themselves are being oxidized, they must be reacting as a reducing agent, because reducing agents cause something else, another species, to be reduced, and they are themselves oxidized. So the iodide ions are acting as our reducing agent, and the sulfuric acid will be acting as our oxidizing agent. And in other questions, that's something that they might get you to identify as well. So for me, if we work out what's been oxidized and reduced, that part of the definition is the most helpful. Okay, then we need to state the change in oxidation state of sulfur that occurs during this formation of H2S, and deduce a half equation for the conversion of H2SO4 into H2S. So let's just sort out the oxidation states first. So H2SO4 and H2S. So the H2S is a little bit more straightforward. So we've got each hydrogen, which is going to have an oxidation state of +1. Again, as a compound, overall the oxidation state would have to be 0, so therefore the sulfur has to be -2. That's the only way that we can get the overall charge to be nothing there. In H2SO4, only a little bit more difficult because we've got a bit more maths to do. We've still got 2 atoms of hydrogen, which are each going to be +1. We've got 4 atoms of oxygen, which are each going to be -2. And then we need to do the maths to figure out what the sulfur is going to be. So we've got 2 plus 8 minus, so we're down at 6 minus, and again overall we need to bring it to 0, so therefore the sulfur here has to be +6. Now that is quite a big change in oxidation state, and only the iodide ions can do that. The bromide ions can reduce the sulfur from +6 in H2SO4 to +4 in SO2, which is still decreasing the oxidation state, but nowhere near as much as it is here. Iodide ions could also reduce the sulfur down to pure elemental sulfur, which would have an oxidation state of 0, which again is a much bigger change in oxidation state. This is the biggest change in oxidation state we can have for sulfur, and the iodide ions can cause that. So change in oxidation state +6 to -2, so a difference of 8, which is crazily big. And then I'm going to use what I've already got here to put the half equation together. So I'm going to put my arrow between the two of them. And this is how I would do this in an exam question. I'm not showing you like this and then me going away and doing something different. I would always write the starting material, the product, leave a gap at both sides after the initial species, put your arrow in, and then you can add the things that we need to each side without having to do all of that in your head first and then write it all out in order. So step 1 of writing any half equation is to balance all the atoms that are not hydrogen or oxygen. So the sulfur in this case, that's already balanced. So step 1 is already done for us. Step 2 is to balance out the oxygens by adding water where relevant. So we've got 4 oxygens on the left and none on the right. So I'm going to have to add 4 H2O on the right hand side to balance out my oxygens. Then step 3 is always to balance out your hydrogens by adding H+ ions where necessary. So we've got 8 H's there, plus the 2 there is 10. On this side we've only got 2, so we need to add 8 H+ onto the left side. And the final step is then to add electrons to balance charges. So the charge on the right hand side is 0 because we don't have any ions, we've just got 2 compounds, so no charge, no charge. On the left hand side currently we've got no charge for the sulfuric acid, but we've got 8 H+. So to make the charges be the same on either side, we have to add the electrons to the left side to bring the charge of these 8+ essentially back down to 0 with the electrons. So the charge on both sides is 0. Now the charge on both sides doesn't have to be 0. It might be that on one side it's -2 and then you have to make the left hand side decrease its charge to -2. So you've got to be careful where you put the electrons, and it is about making sure whatever charge you've got on the side you're not putting the electrons is then balanced by the side where you're putting the electrons. So plus 8E minus. We should then have our half equation. Now it should always be balanced in terms of atoms, which is kind of what we've just been doing in terms of filling in the waters and the H+, so that all looks good in terms of balancing. The charges should be the same on both sides, which they are, so that's us done. Just going to go back through and check I haven't missed anything. 2 observations: what happens to the iodide ions in terms of electrons, state of change in oxidation state of sulfur, and deduce the half equation. I think we're good. I think we are good. So that would be 5 marks there. As always, if anyone has any questions at all, please do not hesitate to get in touch with me, and I'll be back tomorrow with the answer for question 13 at the bottom of this page. Thanks so much for watching, guys.